Deep inside a metal chamber, banks of capacitors discharge in a fraction of a second. A flash erupts, and from a polished red crystal, a perfectly organized stream of light slices through the darkness. This synthetic gemstone, a material often associated with jewelry, serves as the origin point for technologies that map cities, that guide missiles, and manufacture microchips. Before 1960, this level of control was impossible. For most of human history, light was disorganized. Whether from a candle flame or the sun, light waves constantly drifted out of synchronization. This chaos begins at the atomic level. When atoms release energy, they emit photons randomly and in every direction. They act like billions of independent musicians playing different songs at different tempos, without a conductor to align them. Without a mechanism for synchronization, light could not be concentrated into tiny areas or used to carry information with precision. The random nature of atomic emission represented a firm physical boundary. In 1917, Albert Einstein proposed a theoretical path forward. While exploring quantum theory, he realized that atoms might not only emit light spontaneously. He proposed stimulated emission. If an incoming photon strikes an atom that is already in an excited state, it triggers the release of a second identical photon. 1 creates 2, 2 create 4, 4 create 8. The process cascades exponentially, creating perfect synchronization across a massive number of atoms. While the mathematics were elegant, the concept remained on paper for decades. A theoretical possibility is not an engineering system. Einstein provided the blueprint, but he left scientists with a difficult question. How do you actually force millions of independent atoms to cooperate simultaneously? The primary obstacle was thermodynamic. Under normal conditions, most atoms occupy their lowest energy state. Nature resists keeping atoms in the excited states required for stimulated emission. To create a cascade, engineers needed a population inversion, more atoms in excited states than stable ones. This is analogous to balancing millions of spheres at the tops of hills simultaneously. Any disturbance causes a collapse. While others pursued exotic theoretical materials, a physicist named Theodore Maiman focused on the engineering realities of an existing material, ruby. Ruby is aluminum oxide embedded with tiny concentrations of chromium atoms. These chromium impurities act as microscopic quantum systems that can absorb energy and later release it as red light. Maiman's challenge was one of precision manufacturing. Natural gemstones contained defects and cracks that scattered light. To store and amplify energy, the ruby crystal had to approach structural perfection. Engineers began growing synthetic ruby crystals in high-temperature furnaces. They had to maintain stable temperature gradients and minimize contamination to ensure the resulting rods could function as precision quantum devices. Even with improved crystals, early prototypes failed. Capacitors exploded, flash lamps shattered, and mirrors degraded. If optical losses consumed energy faster than the atoms could amplify it, the light collapsed. The final assembly consisted of a synthetic ruby rod, a helical flash lamp wrapped around it, and highly polished end surfaces acting as mirrors. When the flash lamp fired, intense light flooded the crystal. Chromium atoms absorbed the energy, and a population inversion developed. For a brief moment, the system balanced on a knife edge. Stimulated emission began. Photons raced through the crystal, reflecting between the mirrors and triggering additional emissions with every pass. Amplification exploded. On May 16, 1960, the first working laser emerged. The event lasted only an instant, but it proved that humanity could synchronize light at the atomic scale. Transitioning from a laboratory breakthrough to a global technology required a massive shift in scale. Engineers moved from proving the physics to building the industrial infrastructure necessary for mass production. This required crystal growth facilities, vacuum coating chambers to deposit nanometer-thick mirror films, and clean rooms to prevent microscopic contamination. As this infrastructure matured, the applications for synchronized light multiplied. High-power beams were integrated into industrial systems capable of cutting steel with extreme accuracy. In medicine, lasers allowed for less invasive procedures, using light to perform surgery at microscopic levels that were previously inaccessible. This synthetic gemstone eventually helped create the manufacturing systems required for modern microchips. By manipulating light with nanometer precision, the laser became an essential tool of the information age. The descendants of the ruby laser, including gas, semiconductor, and fiber lasers, now form a global nervous system, carrying information across vast fiber-optic networks. Today, billions of lasers operate invisibly within modern data centers, inside our smartphones, aboard orbiting satellites, and scientific laboratories. We are now pushing towards new technical thresholds. Engineers are developing lasers powerful enough to trigger controlled fusion reactions and optical systems for secure quantum communication networks. The success of the ruby laser established the fundamental methods for controlling light. As we seek greater precision and higher power, that same pursuit of atomic-scale control continues to define the future of technology.